Welcome to our next session, everyone. First, we would like to recognize all of our sponsors that help make this virtual workshop happen. Thank you for supporting this workshop. Also, a reminder that you should complete your evaluations for each session. This helps us improve next year's event. Evaluation completion is also necessary to qualify for PDHs. Let's get started with the next presentation. Hello, my name is Steve Popke. I work for the Wisconsin Department of Transportation within the Bureau of Project Development in the Methods Development Unit, otherwise known as MDU. Currently, I assist with training development and design model standards, along with reviewing contractor data packets. Before joining WisDOT, I worked in the civil engineering consultant industry as a design engineer and project manager. My presentation today is WisDOT Civil 3D Site Distance Tools and Workflows. Whenever we develop a highway project, the site distance is reviewed for existing and proposed conditions. Site distances are evaluated in terms of stopping site distances, decision site distance, passing site distance, and intersection site distance. Providing adequate site distance is a key component in providing a safe and comfortable driving experience for the traveling public. Analyzing site distance used to be a very tedious task. However, using 3D tools, this investigation and documentation has become much easier. Civil 3D does include some tools for checking visibility. However, WisDOT has developed its own site distance tools to more efficiently conduct this analysis. Custom tools have been designed to provide the output needed for reviewing site distance based on the WisDOT Facilities Development Manual and AASHTO standards. Let's review some terminology before we look at the tools within Civil 3D so we have a better understanding of what analysis is being performed. First of all, we have stopping site distance. This is the length of the roadway in front of the driver that is continuously visible and is sufficiently long enough to enable a vehicle traveling at or near the design speed to stop before reaching a stationary object in its path. It's the sum of two distances, actually, the braking reaction distance and the braking distance itself. Next, we have decision site distance. This is the length of roadway in advance of a driving decision point that a driver must detect and process changing roadway geometry or controls in order to safely complete the necessary maneuver. And then, depending on the type of roadway that is being evaluated, they either fall into Category 1 or Category 2. Category 2 is set aside for more complex design projects. Here's another graphic within our FDM indicating where you would analyze stopping site distance and decision site distance based on the different categories. The areas highlighted in blue would be evaluated for stopping site distance or for Category 1, and the areas highlighted in yellow would be evaluated for stopping site distance as well as decision site distance for Category 2 if that was applicable for your situation. There are also other examples within the FDM indicating where these different types of analyses would be needed. Next, we have passing site distance. This is the minimum length of roadway that must be available to enable the driver of one vehicle to pass another vehicle safely and comfortably without interfering with the speed of the oncoming vehicle traveling at the design speed, should it come into view after the overtaking maneuver is started. In this area I have highlighted in orange, and you can see it is evaluating the eye height from the one vehicle to the eye height within the approaching vehicle. These are the values that will be used in the check site distance tools based on design speed. This is a screen capture from the WisDOT Facilities Development Manual. They're also found in AASHTO's 2018 policy on geometric design of highway streets, otherwise known as the Green Book. The first WisDOT tool that we have is the Check Profile Site Distance. Its intended use is for scoping and initial design. It is used to check site distance obstructions along a profile, and that's it. It doesn't account for any roadway geometry or obstructions created by the surrounding proposed or existing topography. The eye height used is 3.5 feet above the analyzed profile, and this is hard-coded right into the tool. Let's take a look. So we have a project that we're looking at, say maybe it's in scoping and we're determining what we're going to do, or it's in the early stages of design, and all we have is an alignment. Maybe we have some as-built plans that we can use to establish a profile, to do some site distance analysis, but in this case, say we don't have that, and all we have is some survey information that was taken along the center line. So we're going to use those survey shots to create a profile and then do our site distance analysis. So if I take a look under my survey tab, we do have a survey database. So I'm going to open that to read that information. And I do have some centerline information or a query set up already. So I'm just going to drag and drop that into my file. Now it's loading the point information that was taken from that survey. And I get those points and that survey figure line for the center line. Now to do the analysis, I see I have some shots along the main line and the side road. So I want to query that information just to get the information along the main line. To do that, first I'm going to take a look at these points on the Prospector tab. I can see that there's no alignment property information assigned to those points. So to solve that, we can go to our WisDOT Design tab under the Design panel, under Points, and use the Point Station Offset to UDP, or User Defined Properties, for those points. And I'll create a point group. I'm just going to call this the roadway and the survey centerline. And I'll say OK for that to create that group. For the alignments, I just have the one alignment that I'm interested in, so I'll assign that as alignment 1, and then I'll hit apply. And now it assigns that information to those points. I can close this. Next thing I want to do is I want to query this down a little bit further, just so I have points on either close to the center line that exists out there. To do that, I'm going to edit this point group. Under the query builder, I'm going to create a new query, so I have to check this modify query. And to insert row, I'll just right click. To save time, here's the final query in order to just get the points along the main line. Now within that point group is shown in the red circles, and then everything outside that is shown in the white X's. Now that we have the point information, now we can create our existing profile from that. So under the WisDOT tab, Design Panel, Profile dropdown, go to Profile from Points. Now that I have that point group, I have my alignment. Profile style will be the profile existing, and I don't want to give that any labels. Click OK. Runs through all those points and starts creating that existing profile from that information. Nice progress bar on the bottom there to indicate how far along it is in developing that profile. So it takes a little bit of time depending on how long your project is and how many points you have from your survey. So goes along, almost done. There we go. And then it will say process complete. I'm going to close that. And then we can see in the profile view that I've already created that profile shows up within there. I'm going to clean this up a little bit and add my band information at the bottom. I'll just include this one here. And now we have the existing elevations listed at the bottom. So now that we have the profile, now we're ready for the analysis. So if I go to the WisDOT Design tab, Analyze panel, Visibility checks, and check Profile Site Distance. The first thing it's going to ask for is my profile view, so I'll select that. The profile that I'm analyzing is the one I just created. For the stationing, it automatically populates the limits of your profile view, so that's already in there. Otherwise, I could pick those from the screen using these buttons. My check increment, there's no particular standard for that, but I'm going to use a 25-foot increment. And then for my sight distance, I'm going to use a higher sight distance that normally wouldn't be used for this roadway, but just to demonstrate the tool, I'm going to enter in 910. For object height, that is, we have a couple different options to select from there. You can do the stopping sight distance based on a 24-inch object height, or the height of typically for the taillights of the vehicle in front of you, decision sight distance based on that same object height, or passing sight distance, where you saw before it was the eye height from one vehicle to another. So I'm going to select the 24-inch stopping sight distance. The eye height is automatically built into the tool at 3.5 feet. I also have a couple different options for output. I can select as many or as few as I would like. So I'll check these to create a report, and I'll just overwrite one that I already have in here. I can also create a profile that'll show me the available sight distance based on that analysis. So I have a name already created, so I'll just put that in there. Sight distance for this roadway in the eastbound direction for the existing condition. And then we can create sight lines that'll show up along in this profile view. And next I can select the direction of travel. And that also goes into the naming convention for the layers that'll be created based on this analysis. So I'll say OK. And then we see at the bottom there's a progress bar, and it gives the stationing where it's at as far as collecting that information, evaluating that profile. Processing time will vary depending on the length of your project and the check increment distance that was set. We'll just speed up the video a little bit here just to save some time. Now it says that the process is complete. Instead of closing, I'm just going to slide this off to the side. And it does allow me to still work within the model space in Civil 3D, so that comes in really handy. So we can see the output here. The green areas are where the sight distance was met. The red is where we have obstructions, or that sight distance is blocked by this profile. And then you get a readout of the exact lengths along the bottom here, green being met and the red being obstructed. Distance labels that have an asterisk next to them indicate that the tool detected missing profile data within the sight distance range. This can occur when a surface profile has gaps and near the end of a profile analysis range. If I take a look at the layer manager under my sight distance filter, we can see that these layers have now been created, and I see the layers has been named based on the input parameters that I chose when I started the analysis. So nice thing is I can turn this on, these layers on and off. So if I didn't want to see the met part, I could do that. This is a group, so if I say I had to rerun this analysis, it's not dynamic, I want to delete this information, I could just select that group and delete that and rerun the analysis. The other output that we had chose is the report, so if we open that up, we can see that gives the header information, the eye height, the distance that was evaluated, and each increment and the values for that, and then those that were less than the standard value as well. Towards the end, you'll get this message saying that the required sight distance is outside the profile view. So that just happens once it gets towards the end here. There's no more information that I can analyze beyond this profile view that was created. So you'll get that. That's what that message is referring to. We'd also check to create the profile output. So what that is, I already have a profile view set up here. We'll take a closer look at the profile output later on in the presentation. So now that I've completed my analysis for eastbound, I can take a look at the westbound. And to do that is really easy. Since I have the dialog box still open here, I can just click on this button here with the reverse start and end station, and that flips the stationing. That also flips the direction here as well. And all I would need to do then is update my name from my reporting and output. So I can just call that westbound. I just call this westbound here as well. And then I would say OK, and then that would rerun the analysis. So again, this analysis can be done on a design profile or survey information that's collected early on in the scoping or design process. Now that we've reviewed site distance along a profile, I'll next cover 3D analysis. When fully utilizing 3D data, we can perform a better analysis of the obstructions that may impact a driver's sightlines along a roadway. Example obstructions include, but are not limited to, the roadway geometry, which would include the vertical profile, the horizontal alignment, and sometimes the slope of the roadway itself. This also includes cut slopes and embankments, roadside barriers, which includes beam guard, bridge parapets and railings, vegetation. This could be trees or crops or landscaping, buildings and fences, and cars parked in designated parking areas along a roadway. Back in Civil 3D, looking at the same project, I'm a little bit further along in the design process. I now have an existing surface. I've laid out some of my proposed geometry. You can see here I have a longer project in a rural area, and due to the type of project this is, I don't have a lot of topo along this project. So I want to take a look at my potential obstructions when reviewing my site analysis. So since I don't have any topo, I brought in this aerial and I have created these feature lines along some of the areas that may be obstructions for sight lines. As you can see here, if I zoom in, I have a field here. I'm going to say this is like a cornfield and some trees and a building that was built after this aerial photo was taken. And I'm going to use this information based on these feature lines to create some obstructions to do my site analysis. So the feature lines were created. I've assigned elevations to them based on the existing surface. And now we're going to create obstruction surfaces to represent these features. To do that, I'm going to use a WisDOT tool from our WisDOT Design tab under the Design panel. And then we'll go to Surfaces, Create Wall Surface. And what this does, it'll create a wall or a barrier along these feature lines that'll represent an obstruction. So in the command line, I see I can pick a feature line, a survey figure, a 3D polyline. I'll select this feature line. Side to offset, I'll go to the inside. Height, minimum height, or elevation. I'll just select height. The height option will give me a wall surface elevation that will vary to achieve a specified height at all locations along the feature line. For this, I'm going to say it's a cornfield, so let's just say it's, we'll give it a height of 16 feet. Enter the name for the wall surface. I like to use something that describes that feature and then also the relative location of that just to stay organized. So I'll just say this is crops and then the stationing and then it's on the right hand side. And then that creates that wall surface. I'm still in the command that asks me to select the next feature, so I'm going to select this feature line representing the trees. The side to offset, I'll pick on the inside. Again, I'll select height, and for this height I'll just enter in and say 40 feet. And for the name of this one, I'll just say that it's trees. So I'll just enter that in along with the stationing and the side that falls on. And then still in the command, we still have the building left, so I'll pick that. Side to offset, I'll just go to the inside. And for this one, I'm going to pick minimum height. And what that gives me is a wall surface elevation that is a constant elevation based on the specified minimum wall height. So for the building, I'm just going to say 25 feet. And for the name of that building, we'll give it a name of building and then the station and then the side. And now that that's created, and I'll just hit enter again to exit the command. I'll turn off my aerial image since we no longer need that, since we have what we need. And one good thing to do is just check and make sure your obstructions are landing in the correct location relative to the existing surface. So to do that, I'm just going to pick my existing surface and the obstructions that I just created, and then take a look at that in Object Viewer. If we zoom in here, kind of rotate this around, this is looking pretty good. And these are at, I would say, the correct elevation. And you can see how it kind of triangulates through here, but you have this barrier along here for the crops, the trees, and then this building over here. Hit escape to unselect the surfaces. Now let's take a look at the WisDOT 3D Analysis Site Tool. The 3D WisDOT Site Tool is called Check Site Distance. The tool is intended to be used in all phases of design, as long as you have an existing and/or proposed surface information. A 3D analysis is performed, and the eye height is 3.5 feet above the terrain surface, and this is automatically set within the tool itself. So why did Wisconsin DOT develop this tool, since there already is a check site distance tool within Civil 3D? Well, a few of the reasons are the WisDOT tool measures along the eye path and not the alignment. It also allows for multiple obstruction surfaces to be included in the analysis. It also reports which surface is impairing the visibility, so this could be your existing surface or the proposed surface, or even the obstructions that we can also include. And it also labels the site distance achieved along each sight line. A few of the other features that it includes is creating a site distance profile like we saw with the profile tool, quickly analyzing in both directions, and it automatically creates the layer and the naming of that layer when performing the analysis like we saw in the Check Profile Site Distance tool. So let's take a look and see how this works in Civil 3D. If I go to the WisDOT Design tab, Visibility Check, Check Site Distance. And you can see here we get a similar dialog box, the same as what we had for the Check Profile Site Distance. We have the option to select the alignment, the start and end station. This is automatically populated with the starting and ending of the alignment in the file, but we can also pick this from the screen as well, or we can just enter in the stationing. Typically you would evaluate the site distance for the entire project, but just for the sake of time, for this demonstration, we'll just enter in a shorter length. So I'll have a start and end of 490 to 570. The check increment, there's no particular standard for this, but we'll use 25. The shorter this distance, the longer processing time, but you'll also get very good results with this as well. For site distance, we'll use the same as before, 910. And then for the object height, we still have the same options of stopping site distance, decision site distance, and passing site distance, with these object heights being evaluated. A separate analysis will need to be run if there are different design speeds along the project. A separate analysis will also need to be performed if decision site distance lines are needed. For the eye object offset, this is the offset from the alignment. Since our alignment is the center line, we'll pick the center of the lane, or 6 feet offset from our center line. And then this is the additional information we have access to now, is the surfaces. The terrain surface, that'll be the existing surface or a composite surface consisting of the existing and proposed surface. So you can evaluate existing conditions or proposed conditions. In this case, we're just looking at the existing, so I'll select Exist. And then we also have obstruction surfaces, and these are all the surfaces within this file. So in order to select these, I'll just click on them, and you can use Control Select as well to select all the obstructions that will be included in the sightline analysis. Outputs, same as before. We can create a report, so I'll select that location, that file. And I just want to replace the one that I already have. I'll create profile, we'll come back to that later, and create sightlines. These are the 3D sightlines that will be drawn after this tool has been run. And travel direction, again, will select eastbound, and this also goes into the layer naming, which you can see under my sight distance filter. I don't have any layers in here right now, except for the text. So with that set up, we will run the analysis. Nice progress bar at the bottom gives the station where it's at in its processing. It does take a little bit of time depending on the length of the project and what you have set for your check increment distance. So to save some time, I'll just speed up the video until the process is complete. Now that's complete, I'm just going to leave this dialog box open and just kind of move it off to the side. And we can see the sight lines have been drawn here. The green represents where sight distance has been met, and the red is where sight distance has not been achieved. Reviewing these lines, it looks like maybe some of these obstructions may be blocking sight along here, especially around this building. You can see that each sight line is labeled throughout the roadway here. This is annotative MTEX, so it will scale to be more legible. Near the limits of the analyzed surface, distance labels that have an asterisk next to them indicate that the tool could no longer find a surface in the analysis area. Looks like we have some obstructions due to the existing surface down here as well. If I click on this, this is an entire group. So if I had to rerun this analysis, I could just delete all the lines and perform that again, since it is not dynamic. Hit escape to release that. If we take a look at the layers, we can see that the layers have been created based on the analysis that I was running and whether or not the sight distance had been met or is reduced. I can turn the layers on and off again. So if I just want to see what was in red, I can also select this information and look at it in an object viewer. Otherwise, I'll look at this in model space itself by holding the shift key down and the center mouse wheel. Hold that for a second. And then you get a different graphic there that you can use that indicates that it's ready to be rotated around. And this really gives you a good indication of what's going on here. Let me just turn off a couple layers here just to clean things up a little bit. And I'm going to change my viewing to a realistic view. And now it's really cool to see this information in 3D. You can kind of see, what's happening here. I can pan around. I can do the shift and mouse wheel and rotate around. Actually, it doesn't look like the crops were the issue here. Kind of see this berm along here that's causing some obstructions. If I continue to rotate around the roadway, you can see these trees are really impacting what I can see around this curve here, as well as the building here itself. And we also had created a report. Let's take a look at that. Same as before, the header information, what was the sight distance that we evaluated, the eye height, the surfaces that we were evaluating that exist, and then list all the obstruction surfaces included. List the sight distance that was achieved. The maximum value that will be shown here is what you entered into the dialog box. It won't go beyond that as far as sight distance that it reports. However, you can see we did have some reduced sight distance areas, this one being caused by the existing surface that is listed out here, existing surface as well. This is the area where I wasn't quite sure if it was the existing surface or the crop, so it looks like mostly it was the existing surface causing the issue. A little bit of the crops, the trees for sure, the building. I had some holes in that surface. Well, this tool also picks up on that as well and says, I have some surface data was missing, so what I'm reporting for site distance might not be accurate, so might want to take a look at that. And that's where the object was, and then you get to the point where the vehicle is located where the hole in the surface is, so then you'll get this error as far as I point outside of surface. So yeah, it gives you a lot of good information, so you can make a very informed review of your conditions. Now I did want to come back to and create a profile, available site distance profile like we did before. And what I want to take a look at is the available site distance that I have beyond what I have for the standard stopping site distance. If you take a look at this graph, it's representing the stationing along the bottom and the site distance along the y-axis, like what we saw before. And then you can plot out the available site distance and then the standard site distance that you need to achieve. And you kind of perform almost like a sensitivity analysis to see if you're well within the site ranges or if you're very close. And then in this particular example, it's delineated by the category and stopping site distance versus decision site distance. So I'm going to rerun this analysis, select the profile, I'll give it this name. ASD would be available site distance, so I'm looking at something beyond the design stopping site distance. So I'll update this to 1500, and then I can run the analysis. And again, I'll speed up the video just to save some time. Now that this is done processing, we can take a look at the profiles. You can see here in the orange, this is the available site distance above and beyond what's required for this design at the 1500. And then I also had drawn in here previously just a design profile at the standard 910 just for comparison. So you can see here we have plenty of site distance, and then in these particular locations it gets a little closer and then we don't have enough. Since I drew this ahead of time, this profile view ahead of time, I'll have to update this a little bit here. So we'll go in the profile view properties. Under the information tab, we have a site distance profile view style, just for site distance. Profiles within this view are the available site distance and the stopping site distance. And then for the bands, I'm just going to update this with this information for profile 1 will be our available site distance, and profile 2 is our stopping site distance. And I'll say OK. And then at the bottom here, you can see ASD is available site distance of 1500 and SSD is stopping site distance of 910. And you can see here we fall below 910 in the profile view, and this also corresponds to these areas shown in red below. So that completes the analysis for the eastbound. If I wanted to do the westbound, all I would need to do is click on this button to reverse the direction. That flips the stationing, changes the direction. I could update the name for my profile and my output, select this as needed, and then continue with the westbound analysis. Now I can close this dialog box here. We could create sheets from this information. I'll just jump through the key components for creating these sheets. So you can see I created some view frames along here. Next, I used the create sheets command to produce some plan and profile layouts. So this information is kind of fallen on the lower side of this profile view. So another tool that we've developed is WisDOT Design Profile View. profile view elevation range. Asks me to select the profile views. So I'll select all the ones for my layouts. And then it asks, then I can just hit enter to continue with that. It asks for the minimum elevation. I'm going to say 0 to 1600 because I know that'll cover what I have. Determine the height. Same height, just different values. And then you see it comes up with 1600. So now that's adjusted all my profile views and I have my information there. And for my sheets, since I had the view frame set up as a plan and profile, my sight lines, if I wanted to show that, I could do some labeling in here. If I go back to WisDOT design, the visibility check, sight distance palette, that opens up some information that we have available for labeling these types of sheets. So if we wanted to label the stopping sight distance required, we could just add these leader lines in here as well. I'm going to accept that. It says category X, sight distance required, so I can double click in here and change this information as needed. I can also add a bunch of other information from this palette. The last item that we will review is intersection sight distance, also referred to as a clear sight triangle. This is the distance in advance of an intersection that is free of obstructions and that allows a driver to determine whether or not the intersection is safe to maneuver. The distance is determined by the traffic control at the intersection, the design speeds of the intersecting roads, and the geometry of the intersection. On the screen, I have two clear sight triangles drawn. The one in green is for a passenger vehicle that is entering the roadway and will be turning to the right. Therefore, it will need the required sight distance established along this red line. The required sight distance then establishes a line of sight, and then a bounding triangle. Within this triangle is the area that needs to be free from obstructions. The same goes for this truck that will be turning to the left. The red line here establishes the required intersection sight distance to the right, which establishes the line of sight, and that creates the triangle that needs to be free from obstructions. In this graphic, we have an example of an urban situation. There's an approach vehicle at this side road. If they were going to be turning right, they would need an unobstructed view of this area shown in green, or this clear sight triangle. If they were turning left, they would need the area shown to the right in this purple shaded area to be free from any obstructions. The intersection sight distance is along the roadway that the vehicles are approaching along. To determine the intersection sight distance, you'll need to determine a design vehicle depending on the type of roadway and the type of truck based on that roadway. Next, you will need to determine the type of intersection control and what case applies to your intersection. The different cases that you may come across are shown in the list presented. Once you know that information, you'll have your various design vehicles, the passenger vehicle and the truck vehicle. Each of those vehicles have different eye heights, and based on the type of vehicle, they're associated with different times that are needed to make that movement at the intersection. The distance, or the intersection sight distance, can be determined as shown in the list. So why did WisDOT develop this intersection sight distance tool? If we jump back into Civil 3D and go to the Analyze tab, there are the visibility check tools within Civil 3D. The point-to-point tool is available, however it is very labor intensive to ensure good coverage throughout the clear sight window to make sure all the obstructions are accounted for. Also, the line work generated is not in 3D, it's just 2D graphics, and the sight distances are not reported with this tool. If we look at the zone of visual influence, this is another tool that does provide some sight analysis as well. However, there's no way to specify the height that needs to be visible beyond the location of the decision point at the intersection. Another point is that the results are not very specific. For example, areas shaded in yellow are for objects that are partially visible, and this makes it difficult for an engineering analysis. It is also difficult to determine if an object is not visible due to an obstruction or a depression. So if something was, say, a ditch, it would be highlighted the same way as an object was, meaning that the intersection could not be seen from that location. And again, there are no sight distances that are reported within that area. Another tool that could be used would be InfraWorks. However, there would be the need for working between two different programs. There aren't any CAD tools available for a detailed analysis, and there is limited output from that as well. So that's the reason we decided to develop our own intersection sight distance tool. So just to highlight what our Check Intersection Sight Distance tool does, first of all, its intended use is for all phases of design, again, that has surface data, whether that be an existing surface or a proposed surface. It is actually a 3D analysis that is performed, and the eye height is measured from the terrain surface that is used within the tool. Jumping back into our project in Civil 3D, I've done some prep work to review the sight distance at this intersection. I've created some offset lines from my center line alignment. These are 6 feet on either side of the alignment to establish the center of each lane. I've also offset aligned the 12 feet of the lane plus an additional 14.5 feet for decision point along driveways and intersections without a turn lane. And for this particular intersection, since it does have a turn lane, I've added another 12 feet to establish this decision point for this intersection. So if we go back to our visibility check tools, the Check Intersection Sight Distance, we get a dialog box with some similar features from our other Check Sight Distance tools. The first one is the input of the decision point. If I click this button in the command line, it asks for the decision point or at the location where the eye is for that vehicle stopped at this intersection. So I'll select that point, and it says it found it, so I'll hit enter to accept that. The next one is the vehicle path, and it asks for select target path in check direction. So since I was making a right turn here, if I was turning right, my check direction would be to the left within this lane on this side of the intersection. So I'll select that line and hit enter. Next, I will look at this analysis for a car. So 3.5 feet for a car, it would be 7.5 or 7.6 feet for a truck. So I'll leave this at car and enter a sight distance of, for this particular movement and case, this would be 825 just for this example. For a terrain surface, that would be my existing surface, or it could be a proposed surface. For my obstructions, I will select and then do a control select for additional obstructions that I want to review. And then I'll say OK. Three-dimensional lines are created from the decision point to 1-foot increments along the target vehicle path or the intercepting obstruction. Looks like I don't have any obstructions, and it gives me the sight distance that I was able to achieve, which in this case is the sight distance that we need. Since I have everything set up for this movement, let's just look at the truck as well. So I can just switch that to truck and change it to the required sight distance for a truck or that design vehicle, which would be 1030. And I can hit OK again, just rerun that. And now I am getting some obstructions due to this building here, but it will report out the furthest that I can see, which in this case is 888. However, that is short of our 1030. Now I'll check for the other clear sight window or triangle. I'll leave this as truck, and for that movement, that would be for the left turn, that would be 1235. And I will also need to reestablish my vehicle path. So since I am turning left, I will need to check to the right or on this side of the intersection in this lane. And then accept that. And rerun the analysis. So, deselect my existing surface there. And I have some obstructions there. And then since we already have that side established, I'll just do the car quickly as well. And that would be 1030. And that runs again. And it looks like I also had some obstructions there as well. I got a lot of line work here. I can go over to my layer manager and turn off some of these layers that it's created automatically. Those have the ISD designation for intersection sight distance. I just want to take a look at the ones with the truck, so I'll deselect the car, freeze those, and now I just have the ones for the truck for those movements. I can also take a look at this in 3D. I'll do that by holding the Shift key down as well as the center wheel of the mouse. Wait for that cursor to change a little bit there. And now I can rotate that around and take a look. Change this from a wire display to a realistic. And then I can review this in 3D for this truck movement here. As you can see here, it's hitting some of those crops that we had shown in there as an obstruction. It's also hitting this little berm in here along the roadway that's having some impact there. If I rotate around to the other side, you can see where this building's having an impact as well. Just trying to see if you could see above that surface. It's kind of hard to tell from that view. Oh, there we go. You can see that's 7.6 feet above the intersection there. If I want to turn the aerial back on, I go to map aerial. Say I wanted to kind of see through some of this area here. I can go back to my layer manager, select all these layers and change my transparency. Say I wanted to change that, say, to 80. Now if I take a look at it, I can kind of see through, so I can kind of see the grass and some of the things that were within those sight lines. To complete our intersection analysis, we can also look at vision corners. A vision triangle is an additional area clear of obstructions that might block a driver's view of potentially conflicting vehicles for intersections with stop sign control on the side road and for signal-controlled intersections. Their purpose is to provide opportunities for speed adjustments or evasive maneuvers by vehicles on the major highways if vehicles on the minor roads violate the traffic control. On the screen I have some examples of a vision triangle. That's the area shown in gray, and that is supplemental to, or would be in addition to, the intersection sight distance triangle shown in red. And then based on the type of intersection and the posted speeds for the roadway, you would determine those lengths required. To demonstrate how to do a vision corner in Civil 3D, I've laid out some additional lines in blue based on the table and diagram shown in the previous slide, and that is shown in blue, with the different offsets and the required length for the vision corner. So to create that triangle, we can go back into our Check Intersection Sight Distance tool, select our decision point, and accept that. Our vehicle path, I'm just going to select this line I created to create that vision corner or triangle, the one in blue, and accept that. The eye height 3.5, and for the sight distance I just need something longer than this line. In this case it's 210 feet. I'll just put in 500 just to give it something, and for my terrain surface I'll enter in exist. Say OK, and now I have that triangle. And then I can just reselect the other side with this other line in place. And that's the blue line. and hit enter to accept that and rerun that. And now I get the other side. So based on that, I could create a composite of what's needed for a vision corner and my intersection sight distance. I can pick a individual line. Right now this comes up as a group. To select an individual line, maybe say to create a border of that vision corner, I would type in pick style and change that to 0. And now I can select individual lines and create those borders if I wanted to. There are additional sight distance criteria for other design elements, including roundabouts, interchanges, railroad crossings, driveways, and trail crossings. And you can use our WisDOT sight distance check tools to evaluate all of these. Additional information on these tools and workflows can be found on our WisDOT Civil 3D knowledge base. The workflows are found under Design Checks, and then you can see our sight distance analysis workflows there. So with that, I would just like to say thank you for attending this presentation, and I hope you find these tools and workflows helpful in your designs. If you're looking for more information, feel free to check out the knowledge base or contact me at the information shown below. Thank you.